Well, we still haven't gotten to the definition of Jordan algebras in general. But before we do that, I wanted to say a little bit more about special Jordan algebras. That is, Jordan algebras that arise in the context of associative algebras. The last result I wanted to mention along these lines is Clause's theorem. And what this says is, suppose sigma from A to B is a map, let's say an additive map. So that means that it is an additive homomorphism between division rings such that it preserves the identity element and inverses. So these are unital division rings. They both have a unit element, such that sigma of A inverse is sigma of A inverse, and sigma of 1 is 1. Then, the conclusion is that sigma is either a homomorphism or an anti-homomorphism. Now, recall last time what we did is we showed in this theorem of Jacobson and Rickhart's that this conclusion will hold in case sigma is actually a homomorphism of special Jordan algebras. So that is to say, if sigma is actually a Jordan homomorphism, then this result will also follow from the fact that B is a domain. That was the hypothesis for the previous theorem. So it's enough to show that sigma is a Jordan homomorphism. Now, generally speaking, what does that entail? This entails showing, so recall that if I have a map between special Jordan algebras, and I'm regarding these as special Jordan algebras via, well, just in that they are closed under the operations A goes to A squared, and A comma B goes to ABA. They're rings, so they're certainly closed under those operations, but if sigma respects these two operations, then it's a special Jordan map, so it's a Jordan homomorphism. So if sigma of A squared is sigma of A squared, and if sigma of ABA is sigma of A, sigma of B, sigma of A, I'm going to go back to exponential notation for the map soon because this is going to be tedious to write all these things. Actually, we won't really have use for it in this lecture. But so if these two facts are true, then we say that it's a special Jordan map, Jordan homomorphism. But because A actually has a unit, we don't actually, and because sigma is unital, it's actually enough just to check the second one. So note, if the second one is true, then it follows that sigma of A squared, well, because that's the same as sigma of A1A, and that's going to be, let me write that up here, that's going to be the same as sigma of A, sigma of 1, sigma of A, because we're assuming this is true, and that's going to be the same as sigma of A, sigma of A, because we're assuming that sigma preserves the unit element. That's going to be sigma of A squared. So this will actually follow. So that's coming from the fact that A is not an arbitrary special Jordan algebra. It's not an arbitrary subset of an associative algebra which is closed under these operations, but in fact it is a unital algebra in itself. So we have some extra juice to put into the pot. It's enough just to check this is true. So what we'll actually show that we can express this, this composition ABA in terms of some expression involving plus, minus, and inverses. And from that, it will follow that because sigma preserves these operations of plus, minus, and inverses, and it'll follow that because A is a division algebra, and so sticking on inverses on pretty much everything we care to is okay. Everything is invertible. Everything non-zero is invertible. It'll then follow that we have a Jordan homomorphism. Well, before we do that, let me just fill in that just a moment. So note that if A or B is equal to 0, then ABA, sigma of ABA, well, is the same as sigma of 0, if either one of them is 0. And because this is a additive it's an additive map homomorphism, this is just 0. But also we have, we want to, if A or B is 0, then either sigma of A or sigma of B is equal to 0, and so this will also be true. This is also equal to 0. So the fact that these two things are the same in that case is for free. So without loss of generality, in proving everything, we can assume A and B are both non-zero. And so I'm allowed to stick inverses on top of those things. Maybe there's a few other details that will come up, but let me make that observation. Okay, now, to the point of it, we would like to take ABA and rewrite it in terms of the things that sigma actually preserves. The additive structure, the unit element, and inverses. Really just, plus, minus, and inverses, like we said. Okay, so what do? Well, just do it. ABA, I want to basically peel off the layers of ABA in terms of adding and inverses. So I'm going to subtract and add A, and I'm going to just focus on this piece over here. And this will let me pull out. I can certainly pull out a factor of A on the right. But let me also pull out a factor of. Let me also pull out a factor of B. Yeah, I'll work all the way down here and then move to the next slide. Let me pull out a factor of B. So I've got A minus B inverse BA. Okay. Now, not sure how to explain why this is a great idea to do, but this will be easier to work with if I just invert the whole thing. So I'm going to just invert the whole thing. So I'm going to stick inverses on everything and reverse the order. Inverse. But now I've inverted all that, so I put an inverse on the outside plus A. Okay. Now I'm gonna basically pull out an A inverse and pull out one of these, and magically I'll be done. Okay. So, but to make it a little bit clearer how that works, let's see. So I'm gonna actually, let's see how to say this. Let me add and subtract an A. So I'll look at A minus A plus B inverse, A minus B inverse, inverse, inverse. So I've just rewritten B inverse as A minus A plus B inverse. And if I group these guys together, let me continue over here, just so that I don't run out of space. So I'm going to group these a little bit differently. Let me write that as this is A inverse. And then on the inside I have an A minus B inverse. Whoops, this is, no, I'm okay, that's right. An A minus B inverse, close that parentheses, and then I have an A minus B inverse inverse. And that's this one, this one, this one, I need to match those. And on the outside of all that I have another inverse. Okay? Now, what is that? Well, I'm going to take this expression and I'm going to pull out, I'm going to factor out my, factor in, or I guess I'll multiply in these A inverse and the A minus B inverse guy. So, multiplying through the A inverse, that looks easier. I'll get a 1 minus A inverse. A inverse times that is 1, let me just leave it on the outside. I get a 1 minus A inverse, A minus B inverse. So that is this much of the expression right here, times A minus B inverse, boom, boom. Was I off by a parentheses? Well, let me put another one here so that I can put my big inverse on the outside. Okay. Maybe it would look nicer if I wrote some square guys. So let's make this thing a square, just so we can see what the heck's going on here. And this is like the mega big parentheses on the outside. Okay? So that's what we have. We have, okay, now what I'm going to do is I'm going to multiply this guy in. And we're done, right? You multiply this thing in over here, and what do I have? I have a, let me just write my big bracket, and this little thing is a 1, it's an A minus B inverse, it's this times the 1, and now it's this times this thing, but this is the inverse of that, and that's the magic, right? Because I'm just left with this minus A inverse, close parentheses, inverse. Ah, whoops, I dropped my A. Okay. I had this thing plus A, this thing plus A, I still had my plus A, I had my plus A, but I rewrote this thing, and I forgot my plus A. So there's a plus A there, it's this thing plus A, so it's actually this thing plus A. Altogether, what have we shown? That ABA is equal to A minus B inverse, minus A inverse, plus A. ABA is equal to that. Now, that tells us that if this expression on the right makes sense, so let me say it like this. So given A and B such that this is defined, then sigma of ABA is going to be sigma of that whole expression. And because this whole expression is writable in terms of plus, minuses, and inverses, that's going to be the expression evaluated on sigma of all those things, which is going to be sigma of A, sigma of B, sigma of A. Because sigma preserves these operations of plus, minuses, and inverses, I have this. For A and B such that this is defined. Well, now we just have to say, well, what if this expression isn't defined? Then what? Well, why might it not be defined? For example, else, then we either have A inverse or B inverse is not defined. But because we're in a division algebra, that's only going to happen if A or B is equal to 0, and in those cases we've shown that this still holds. So this still holds if A and B are potentially 0. When else might it not hold? It might not hold if A is equal to B inverse, then I can't take the inverse there. If A is equal to B inverse, though, then ABA is A inverse, if A is equal to B inverse, then this is B inverse B inverse, so this is just B inverse. And so sigma of ABA is sigma of B inverse is sigma of B inverse, because we know we preserve inverses. And in that case, we're left with sigma of B inverse is the same as sigma of so sigma of B inverse is sigma of B inverse sigma of B inverse, which is sigma of B inverse, because I preserve inverses again, sigma of B inverse, which is sigma of A, sigma of B, sigma of A. So in this other case, when this expression is not defined, I still have the identity that I need. So these are all the loose ends. I just want to show that sigma of ABA is equal to this for all A and B. If A and B are 0, one of them are 0, we know it's true. If A is equal to B inverse, we know it's true. I just need to check that if this thing inside here is equal to 0, we still know it's true. And if it's true in all those situations, then, so if it's true for all those things, then the only other case I need to know is when none of those things are 0, but then this expression will be defined, and then we know it's true as well. Okay, so the last case I need to check is or, A and B are non-zero, A is not B inverse, but maybe this expression is 0. A minus B inverse is equal to A inverse. Of course, if that's true, then that's also the same as saying that A is equal to A minus B inverse. Well, but if A is the same as A minus B inverse, then you can subtract off A's and find that, so subtract off your A and you get that 0 is equal to minus B inverse. Oh, but if B is invertible, 0 is not going to be its inverse, so this never happens. It never occurs because we've eliminated those kinds of possibilities already. Okay. So, the conclusion is that we do have a Jordan homomorphism. Sigma of ABA is always sigma of A, sigma of B, sigma of A. Because it's unital, we all also know that sigma of A squared is that sigma of A squared is sigma of A squared. So it's a Jordan homomorphism, so by Jacobson-Rickard, we therefore know. So this is a Jordan homomorphism, which implies that sigma is a homomorphism or an anti-homomorphism. Let me state, just because it's good to know, that this identity is pretty famous. It's called Hua's identity. In the usual form, it's written as, how's it usually written? As A minus ABA is equal to, so A minus ABA is the negative of this thing, which I'll write by switching the signs over here. So it's usually written is equal to A inverse minus A minus B inverse inverse inverse. So this is the typical form of Laws identity. Okay, so that concludes this time, and next time we'll actually define Jordan algebras.